come to the next lecture on signals and systems, where we now continue to look at certain properties of the Fourier transform. But before that, let us quickly take a review of what we have done in the previous lecture, which I will request Uday to do.
Begin with, we saw that the Fourier transform of the convolution of xt, the input signal, and the impulse response ht is given by the product of the individual Fourier transform, that is x of omega and h of omega. Secondly, we saw that the Fourier transform is like a system which takes x of t, which is in the time domain, to x of omega, which is in the frequency domain. Then we looked at some of the properties of systems which change by the Fourier transform. As in, causality and memory cannot be spoken about since the independent variable has changed. Boundedness here refers to the convergence of the Fourier integral. Further, we see that the Fourier transform is not bounded. As in, if you take a bounded input signal, we get that the output x of omega is not bounded. Then we saw what is known as the Gibbs phenomena. When we try to approximate an input signal which has certain discontinuities by a Fourier series with finite number of terms, we notice that at the discontinuities, the approximated Fourier transform shows spikes of increasing magnitude when you increase the number of terms. Then we re-examined what we mean by equality of series. We say that two series are equal when the integral over a finite period of time of the square of the modulus of the difference between the input signal and the approximated Fourier transform with increasing number of terms tends to 0. Then we looked at Dirichlet's conditions for the Fourier transform or the inverse Fourier transform to exist. And so that there are three of them. One is the integral. One is the Fourier transform being absolutely integrable. Secondly, that there should be finite number of discontinuities in the input signal. And thirdly, there should be a finite number of maxima or minima in the input signal. Under these conditions, the Fourier transform or the inverse Fourier transform are valid. That's good.
Good. Very good. That was quite a comprehensive and correct summary. I'll just add a couple of points, or maybe modify a couple of statements that were made. I think the summary was very accurate. You see, one has to be a little careful about making definitive statements. For example, I think at some part Uday was referring to the causality, stability, etc., thinking of the Fourier transform as a system operation, right? So thinking of the Fourier transform as a system operation on a signal resulting in a frequency domain representation. So you have xt as the input and capital X of omega as the output. Now, when the input is bounded, the output is not necessarily bounded. That's an accurate statement, because there are situations where the Fourier transform does converge for all omega. So one has to be a little careful in saying that the Fourier transform looked upon as a system is not stable, because there are examples of bounded inputs where the output is not bounded or the Fourier integral doesn't converge. But that's not true for all. So one has to be a little careful in saying that the output is not bounded at all, or whether the output is not bounded in some circumstances, right? Yes, Nirmesh, yeah. Yeah, that's right. So that's another point which I need to correct. We have to be, again, when stating Dirichlet's conditions, he stated them quite correctly. I just thought I should make them, tie up a few gaps here and there. It's not the Fourier transform that needs to be absolutely integrable, it's the signal itself. Now, it depends on whether the signal is periodic or whether the signal is aperiodic. Now, you see, aperiodic could be thought of as a signal with infinite period. So, if it is aperiodic, then you want it to be absolutely integrable over the entire real axis. If it is periodic, you wish it to be absolutely integrable over the period of the periodic signal. Yeah? Because when we talk about a periodic signal, we refer to its Fourier series representation. When we talk about an aperiodic signal, we refer to its Fourier transform. And in fact, soon we shall be relating the two. Yeah? However, one more point, the number of maxima and minima need to be finite over a finite interval. So, you see the objection, you can have an infinite number of maxima and minima in the periodic signal spread over the entire real axis. But when we refer to a periodic signal, the finiteness of maxima and minima refers to one period. So, there must be a finite number of maxima and minima in one period. That is what is needed. Similarly, the finite number of discontinuities need to be in a finite interval for the case of aperiodic signals, and of course for one period in the case of a periodic signal. These are little corrections that I thought I should make in the summary. Otherwise, I think it was an excellent summary, and let us proceed then with that background to look at some properties of the Fourier transform. Yeah. Now, by properties I mean what happens to the Fourier transform when we make certain changes to the signal. That is what we first mean by properties. Yeah. So, let us look at some elementary operations on the signal, and let us look at the consequence on the Fourier transform. Of course, what we shall do is we shall look simultaneously at the Fourier series and the Fourier transform, in the sense the context is different. You know, if the signal is periodic, then we need to refer to the Fourier series and we look at properties of the Fourier series. If the signal is aperiodic, then we are referring to the Fourier transform. Yeah. So, we will take each of the cases in parallel, right, the case of the periodic signal and the case of the aperiodic signal. Now, let us consider first the most simple operation that one can encounter, namely the operation of time shift or shift on the independent variable. By a shift on the independent variable, we mean we replace xt by xt minus t naught. For a fixed t naught, where t is the independent variable. Now, it is very easy to obtain the Fourier transform of xt minus t naught in terms of that of xt. We simply write down the integral. So, first let us assume the signal xt is aperiodic. So, let us look at its Fourier transform. And of course, we will assume that the Fourier transform of xt exists, and if that does, then it is very easy to see that the Dirichlet conditions are also satisfied when it is shifted. Shifting does not affect satisfaction of the Dirichlet conditions. Now, all that we do is to make a change of variable. So, we write t minus t naught is equal to lambda. This substitution, one can easily make the substitution and show that this is e raised to the power minus j omega t naught times capital X of omega, where capital X of omega is the Fourier transform of the signal xt. All right. So, what is the effect of time shift? The effect of time shift is to multiply the Fourier transform by a quantity given by e raised to the power minus j omega t naught. It should be emphasized that this quantity has a magnitude of 1 for all frequencies. So, if we look at the magnitude of the Fourier transform, it remains unaffected. What changes is the phase of the Fourier transform. And how does the phase of the Fourier transform change? It changes by an amount of minus omega times t naught. The change of phase is proportional to omega. The change of phase is minus t naught times omega as a function of omega. Now, because of this change of phase is said to be linear phase. So, we say that the effect of shift in time is to add a linear phase to the Fourier transform. This notion of linear phase finds importance in a wide spectrum of situations. So, it should be understood right at the start what we mean by linear phase and what it implies in time. Right? Linear phase, addition of linear phase in the spectral domain implies a shift by the same, well, it implies a shift in time of the whole signal. So, it is equivalent to saying that all frequency components, all omegas are shifted by the same T naught. Right? That is another way to interpret it. Well, it's already wet. Scrub it. Terribly त्यांना सांगा की जस्ट कीप थोडंसं केरोसिन ठेवत जायचं. इट इज इझी टू रब केरोसिन. Bearing with us patiently in the event of taking a little longer to wipe the board than usual, and let's proceed then with the discussion of the second property of the Fourier transform, where we'll now look at the property of duality. In fact, I thought I'm quite fond of that property. I know it could be discussed a bit later, but I find that a lot of explanations about Fourier transform behavior can be very neatly given with the idea of duality. So, we'll come to it soon enough. Right? So, we'll now consider the property of duality. Now, duality refers to the dual nature of the Fourier transform. By dual, we mean that in a sense the Fourier transform can also behave like a signal. You will understand what we mean by that. And duality follows from the similarity in the nature of the forward Fourier transform relationship and the inverse Fourier transform relationship. So, let's look at the forward and inverse Fourier transform relationships. the forward Fourier transform, and the inverse Fourier transform. Now, we had already pointed out that there was a great deal of similarity between these two transforms, these two relationships, right, in the sense that if you really look at it, it's almost as if the roles of omega and t were reversed in this integral, except for a constant factor, Now, in fact, what we shall do is, we shall even get rid of that constant factor. A very simple transformation will enable us to do that. Suppose we replace omega by its Hertz frequency. Omega is like an angular frequency. So, we could replace it by its Hertz frequency, right. So, we could write omega is 2 pi f, in which case I shall straight away make the replacement here. Now, I will write capital X of f here, though of course you must interpret it properly. When I write capital X of f and capital X of omega, it does not mean that I am equating omega and f. I am just saying that you replace omega by 2 pi f, right. So, even here we will write df, and you see, since omega is 2 pi f, there is a 2 pi df, right. So, we have a df and a 2 pi coming out, all right. So, this 2 pi divided by 2 pi cancels, and we have just xf e raised to the power. Now, of course, here we could replace in both places omega by 2 pi f, right. So, we have xt e raised to the power minus j 2 pi ft dt and xf e raised to the power j 2 pi ft df, all right. So, now the symmetry is so much stronger, yeah. So, maybe let us make those replacements here. All right. Now, in fact, here one can notice a precise symmetry. The 2 pi is absent. In fact, if you notice here, except for the negative sign, the two equations are almost identical here, right. The two equations are almost identical except for the negative sign, yeah. So, in fact, let us make a statement. You see, suppose you think of this instead of as an inverse transform relationship, as a forward transform relationship. So, let me rewrite this equation with the role of f and t reversed, right. So, I mean, here of course this is x of f, right, this is capital X of f, and this is small x of t, yeah. So, let me rewrite this with t and f reversed. So, I will say integral x of small x of f is Now here we could write, you see, in fact we can simply write, simply write small x of minus f. Yeah. So you see, the small change that we can make here is that since we want a negative sign on this integral, we could consider small x of minus f instead of small x of f. Is that right? So we could write small x of minus f is xt e raised to the power minus j 2 pi ft df and dt. Is that right? Is this equation clear? What have I done? I have simply reversed the roles of t and f. So I have written capital X of t e raised to the power j 2 pi tf dt, okay, and I have, instead of evaluating at t, I have evaluated. See, now here, if I reverse the roles of t and f, this becomes f. So if I evaluate that expression at minus f, it gives me this expression. Is that right? Is it fine? Right? This is fine. So what is the statement that we are making here? You see, now in the language of, see here, now if you think of the Fourier transform as a function of the Hertz frequency f instead of the angular frequency omega, right? Then what are we saying here effectively? We are saying that if xt has the Fourier transform capital X of f, right, then capital X as a function of t has the Fourier transform small x of minus f. Is that right? Now, in fact, this is also a reflection on so many other things about the Fourier transform. For example, just as we have a duality on the relation, that is, just as xt leads to capital X and capital Xt leads to small x. I mean, what does it say? It says that if you look at the function and its Fourier transform, and if you look back at the Fourier transform thought of as a function in time, then there is an intimate relation between them. So you see, this is, please note, duality is a statement quite different from Fourier transform and inverse Fourier transform. I mean, it's a different thing to say that if I have a given Fourier transform, a given xt corresponds to it. That's a different story altogether. What we are saying here is that if I know one Fourier transform pair, I also know immediately another Fourier transform pair, right? So, if I think of a table of Fourier transforms, right, then my need to remember the table goes down by a factor of half, right? Because if I remember one pair, then another pair automatically gets covered, right? Let's take an example. Let's take an example to illustrate the point. Now, let us obtain the Fourier transform of the function which is constant in a certain interval, right. So, let us take a function that looks like this. So, you see, the thing is, this particular function has a great deal of importance in a number of different situations. In fact, not only does this function have an importance, a Fourier transform of this form also has a lot of importance in a wide class of contexts, right? So, it's worthwhile looking at this Fourier transform pair in great depth. Now, let's obtain the Fourier transform. So, here it's very simple to evaluate the Fourier transform here. It's simply minus t to plus t a e raised to the power minus j omega t dt, all right. A is a constant, all right. So, this can be rewritten as a e raised to the power minus j omega t. This is a very simple integral to evaluate. Right. Now, this is extremely easy to evaluate. So, this can be written as, in fact, let me write it here. A e raised to the power Yeah, so we can remove the minus sign if we reverse the order of the integrals. Is that right? All right. Now what is this expression? This is nothing but twice j a all right. All right. This is the expression for the Fourier transform. All right, let's sketch the expression. Let's sketch how this expression looks. Now, of course, I agree that this integral is not valid as omega tends to 0, in the sense that, either we should, write a separate value for omega equal to 0, or we should ascertain whether this has a limit as omega tends to 0. In fact, it turns out this has a limit as omega tends to 0, and that limit is equal to the value of the integral at omega equal to 0. Yeah? So, in fact, we can write it very easily if we simply note that this can be rewritten by cancelling the j, and we have twice a sine omega t. So, we will write it in a standard form, sine omega t by omega t, and we also bring a t to the numerator. So, we write it in this form. And we rewrite this now as twice a t sine pi into 2 f t. We will write it that way. Divided by pi into 2ft. All right. Now, this can be written in the form twice at sine pi x by pi x, where x is equal to 2ft. The function sine pi x by pi x has a great significance in signal processing, right? In fact, we give it a name, we call it the sinc function. So, sinc x is defined by sine pi x by pi x. Let us sketch the sinc function. Let us sketch the sinc function. You notice that the sinc function is an even function of x. So, sinc of positive x is equal to sinc of negative x, or sinc x is equal to sinc minus x. Yeah? That is because both of them are, you see, actually the numerator and denominator are both odd functions here. So, you see, not only that, you also recognize the nature. See, if this term were to be absent, sine pi x would have been an oscillatory term. So, we expect there are going to be decaying oscillations with a decay envelope of 1 by x. However, we must be careful about x equal to 0. You see, as x tends to 0, it is very easy to ascertain by using L'Hopital's rule or otherwise that this function tends to 1. Right? That could be ascertained either by using L'Hopital's rule, where you differentiate the numerator and denominator, or it could be ascertained by expanding this in its Taylor series, right, and then taking the limit as x tends to 0. Alternately, you could also establish it by looking at the integral itself, the Fourier integral. So, one can separately evaluate the integral at omega equal to 0 and ascertain the value. Yeah? But here, at x equal to 0, the value is 1, and subsequently, the behavior is something like this. At every integer, other than 0, it takes on the value of 0. In fact, the 0 crossings, so to speak, are at all the integers other than 0. There are no other points which are 0. Yeah? This is as a function of x. We are plotting it as a function of x. So, needless to say, when x is equal to 2ft, the 0 crossings shall occur when 2ft becomes an integer, or when f is an integer multiple of 1 by 2t. Right? It is an integer multiple of 1 by 2t. Now, what is the significance of 2t? 2t is the interval of the pulse. You might think of that time function as a pulse between minus t and t. So, the interval of the pulse is 2t, and at every multiple of the reciprocal of the interval. So, you might think of the reciprocal of the interval as measuring some kind of a frequency, right. So, at every multiple of the reciprocal of the interval, you get a null in the spectrum. So, these are called, so these terms, it's a good idea to get familiar with some of these terms. A null in the spectrum. A null in the spectrum means a point at which the magnitude of the spectrum falls to 0. Yeah. So, in fact, now it's not too difficult to see what kind of a pattern this will give you. This will simply give you this sinc pattern multiplied by a factor of 2 times at, right. And then one can keep So the nature, the shape of the pattern is the same. Now what I want to bring out through this example is that now we know the Fourier transform of a pulse. A pulse is a function that is constant for a certain interval of time and 0 otherwise. But with it, because of duality, we also know the Fourier transform of a pattern like this. So what it tells us is that a pattern like this is called a sinc pattern, right? It's also called a sampling function. Now, it will not be clear to us at this moment why it's called a sampling function. We shall understand later when we talk about sampling. But it's a good idea to know that this is also called a sampling function or a sampling interpolator, right? So this sinc, but the more common term used is sinc. So, people call it a sinc function. The inverse Fourier transform of a the Fourier transform of a sinc function, therefore, is a spectrum which is flat over a certain range of frequencies. In fact, what was the precise statement we made? We said that capital X of t, so if you think of this as a function in time now, has a Fourier transform small x of minus f. Now, what does minus f do? It inverts the spectrum with respect to the f-axis. So, it mirrors the spectrum about the point f equal to 0. But in this case, the function is symmetric about t equal to 0, and therefore mirroring has no effect. And therefore, it has precisely the same kind of spectrum. Now, in fact, that spectrum, as I said, has an importance by itself as well. Just as the pulse has a great importance in signal processing or in communication or in a number of different contexts in the analysis of signals and systems, not necessarily electrical engineering contexts, the spectrum which is constant in a certain range of frequencies also has a very important physical significance. In fact, it corresponds to what is called an ideal filter. So, if a system has a spectrum, has a behavior like this, if an LSI system is stable, that means its impulse response is absolutely integrable. And the Fourier transform of the impulse response, which is called the frequency response, we gave it that name last time, didn't we? We said that the Fourier transform of the impulse response is the frequency response. A frequency response like this a frequency response that looks like this, a function of omega here, or as a function of f. Now, what kind of a frequency? I mean, what are we saying qualitatively about the frequency response here? The frequency response is constant. It has a magnitude of, in fact, it has a value of a, not just a magnitude. It has a value of a between minus some omega 0 and plus omega 0, and it's 0 outside. Yeah. Now, this is the frequency response of what is called an ideal low pass filter. Right? So an ideal low pass filter. All right? In fact, here we would now like to bring in the notion of filters. Yeah? You see, we've seen that at least a subclass of linear shift invariant systems whose impulse response satisfies the Dirichlet conditions can also be associated with a frequency response. Now, what is the physical interpretation of a frequency response? A physical interpretation is that it takes the spectrum of the input signal and multiplies it pointwise by the Fourier transform of the impulse response. So, you see, the idea is, it's as if you have a fixed way of modifying the spectrum for all input signals. For example, what would a linear shift invariant system with this frequency response do? It would retain all the frequency components from the input signal between minus W0 and plus W0, and it would reject all of the others. And for the frequency components between minus W0 and plus W0, they would all be uniformly multiplied by the constant A. That is the interpretation, right? So you see, there are two things. One is that you have a decoupled action of each frequency omega, and that decoupled action is independent of the input. That's very important. So when we talk about frequency response, it's very important to realize that the action or the frequency response is independent of the input that is being given. That's why one can talk about the frequency response of a system and not the frequency response of a system given the input. Yeah? And this holds only for linear shift invariant systems. In fact, I'll go a step further. It's only for linear shift invariant systems where it is true that when you put in a sine wave of a given frequency, let's say frequency omega equal to omega 0, that the output is also a sine wave of the same frequency, omega equal to omega 0. This holds only for linear shift invariant systems. What can change is the amplitude and phase. And what does the frequency response of a stable linear shift invariant system tell us? At every point omega, it tells us the change in amplitude and the change in phase which a phasor with that frequency would undergo. One must be very careful. You see, what is the interpretation, or what is the significance of a particular point f here? The significance is, if I choose a particular point f here, suppose f is equal to W0 by 2, then the frequency response is A by 2 at that point. What does it mean? It says that if I have a phasor of frequency 2 pi f0 by 2, or angular frequency omega 0, right, given by 2 pi f0 by 2, what comes out of the LSI system is also a phasor of the same angular frequency, but amplitude multiplied by capital A. Phase is unchanged because the phase of this, well, phase is unchanged if capital A is a positive number. If capital A is a complex number, then the amplitude is multiplied by the magnitude of A, and the phase is modified, or to the phase is added a term equal to the phase of A. So for example, suppose A were equal to 1 plus j, right? 1 plus j has a magnitude of square root of 2 and a phase of 45 degrees. Then what is the interpretation? It means that all phasors between 0 and omega 0, between 0 and W0, all phasors whose frequencies are in fact between not just 0, minus W0 and plus W0, undergo an amplitude change of mod A, which is square root of 2. So the phasors are all multiplied by square root of 2 in amplitude, and they all have a phase shift of 45 degrees. Now this also brings us to the requirement of the Fourier transform of real signals. When we talk about phasors, we will also immediately gain an insight into the Fourier transform of real signals. Now you see, how do you get a real signal? You get a real signal if you have phasors where for every phasor of frequency omega 0, there is an equal and opposite phasor of frequency minus omega 0, right? I mean, you have to, if you want real signals, then they must be composed of real sinusoids. Each sinusoid has two phasors in it of equal and opposite angular frequencies, plus omega 0, minus omega 0. So you see, the point is that if you look at the spectrum of a real signal, And if you look at corresponding points on the positive and negative sides of the real axis, they correspond to phasors. Let's say the positive and negative points are plus omega 0 and minus omega 0. The amplitudes of the 2 points must be the same, and the phases must be exactly the opposite. Is that clear? Yeah? The phases must be exactly the opposite, the amplitudes must be the same, right? Now let's prove this formally in the Fourier transform. Yeah, let's prove this in the Fourier. Yeah? So, what are we saying? We are saying xt is real, and we are looking at its Fourier transform. So, xt e raised to the power minus j omega t dt. Okay. Now, in fact, what we will do is we will prove an auxiliary result. We will consider the Fourier transform of x bar t. Right? Let us consider the Fourier transform of x bar t. Right? This is the Fourier transform of x bar t. Now, we will rewrite this in the following way. We will rewrite it as integral xt e raised to the power j omega t, but we will write minus j omega minus t, or that is right. Is that right? We write it as xt e raised to the power, well, this, I am trying to put the complex conjugate on the whole integral. So, this becomes e raised to the power j omega t, but I am writing it as e raised to the power minus j minus omega because I wish to see it in the form of a Fourier transform. Yeah, so this is nothing but capital X, that's the Fourier transform, evaluated at minus omega and then complex conjugated. Is that right? It is the Fourier transform x evaluated at minus omega and then complex conjugated. Yeah? So, that means if this in fact brings the property of the Fourier transform. xt has the Fourier transform capital X of omega then x bar t has the Fourier transform capital X minus omega bar. Now, if xt is equal to x bar t, that means that the signal is real, then x omega is equal to x bar minus omega. That is exactly what we are saying. Right? If xt, if the signal is real, then x of omega is equal to x bar of minus omega. So, when you take corresponding points on the positive and negative sides of the omega axis, they have the same magnitude, but opposite phase, which is to be expected as we explained. Now, I thought I should spend a couple of minutes in discussing this point. It is very obvious when we see this point written down in this fashion. Believe me, I have been asked by innumerable students, either from IIT or outside, about the significance of negative frequency. In the sense that, you see, here we are talking about positive and negative frequencies, omega, right? And it is a very common confusion in the mind of a student who studies signals or who analyzes systems as to what significance a negative frequency can have. I mean, we can visualize positive frequency. So we tend to have some acceptability for the positive side of the frequency axis, but we say, well, what does negative frequency mean? Well, before I answer the question, maybe let me ask you, what can, firstly, what do you understand by negative frequency? Or is there something sacrosanct about positive and negative here? And why are we using both positive and negative? What is the physical interpretation? Yeah, you can pass the mic.
The direction in which the rotation of the phasor is there, it signifies the positive and negative omega.
That's right. Very good. That's very correct. That's very correct. As Abhishek says here, you see, it's the direction of rotation of the phasor which denotes the positive or negative sign, right? So, if the phasor rotates in the anti-clockwise direction, you talk about it as positive frequency. If the phasor rotates in the clockwise direction, you call it negative frequency. Now, in that case, I ask a further question. Is there any difference in status, quote unquote, between positive and negative frequencies? Is it that one of them is physically meaningful and the other one is not? Or are both of them not really physically meaningful? Or is it that there are two physically non-meaningful things that result in a physically meaningful thing here? You see what I mean? I mean, people tend to think, see, it's like saying, well, sine omega x, I can understand what sine omega x means. What does sine minus omega x mean? I can't see why I should have a sine minus omega x. So, why are we bringing in positive and negative frequencies? That's the further question that I wish to ask. Now, I'm asking this question, I thought we should spend some time discussing it here, because this is a question that is commonly raised by students later when they encounter this in other situations. And it repeatedly occurs to them that there seems to be something that is physically not meaningful. So, can one take this argument further? Why then positive and negative? Is it that only one of them has a physical meaning? Right? Anyone would like to? Yes, Harshit? Yeah? Would like to? Would like to answer? Yeah. Yeah, good. Very good. So, see, the point that Harshad brings out clearly is that a sine wave has two phasors in it, right? So, each sine wave that you construct to make a real signal requires two phasors. So, either one could say that both the positive omega naught and the negative omega naught, both are physically non-meaningful, in the sense both of them are complex numbers. They are not really signals as we see them. But together these result in a meaningful thing. Because when you add up two complex numbers rotating in opposite directions, starting from equal and opposite phases and with the same amplitude, they result in a sine wave. So, it amounts to saying that two complex phasors give you one real sine wave, and that's why we need the notion of positive and negative frequency, right? This is a very important point which I thought we should record and keep in our understanding, because it is a common source of misunderstanding in later courses or in later discussions where we encounter the spectrum, all right? So, this is one more property that we've seen in the context of the Fourier transform. Yes, yes.
Positive frequencies also will be wrong. If you have a filter which has been localized about say plus omega naught,
Yeah.
and for negative value it's 0.
Yeah. So, you see you're right. I mean, what Samir says is that it is not even correct then to say that positive frequencies have a physically meaningful interpretation. Actually, either one can say neither positive nor negative frequencies have a physically meaningful interpretation, in the sense they don't correspond to a physical reality. It is their combination that corresponds to a physical reality, right? So they cannot be separated from one another. That's the way we look at it. I mean, a positive and negative frequency cannot be separated from one another in a real signal, because they combine to make up a real sine wave. Yeah? So today we have looked at the following properties of the Fourier transform. We have looked at the effect of a shift in time. We have looked at the duality property. And we have looked at the effect of complex conjugation on the signal. Right? Now we shall take on further the properties of the Fourier transform after a couple of lectures. We shall make use of the next 2 lectures to solve some problems related to the topics that we have done so far. Yeah, and we shall take further on 2 lectures hence about the Fourier. However, we shall have 2 more sessions now, but related to the solving of problems. Yeah. Thank you so much, and we conclude the lecture here. Now, just a moment. Tomorrow we'll take